Hi guys, good morning. Welcome to the Aerospace Structure Lecture series. So today we're going to see about the strain energy in the structural members. So here we are going to see what is the strain energy method to finding the deflection of members by using of axial load, bending load, shear load, and torsion load. So in introduction, in mechanics, energy is defined as a capacity to do the work, and work is the product of force and the distance which move along its direction. In solid deformable bodies, the trusses multiplied by the respective areas or the forces and the deformation or the distance. The product of this force and deformation is the internal work done in a body by extremely applied forces. The internal work done is stored in the body as the internal elastic energy of deformation or elastic strain energy. So conservation of energy, work and strain, the relationship we can see as the conservation of energy is one of the basic law of physics, and it is a closed system consisting of a structure and its applied forces must obey its law. So work is equal to energy stored in the body and energy losses. That is W equal to ES and EI. So now in the structures, work is performed by the external load moving through a distance, and the energy is stored due to the elastic deformation of the member. If the structure is static, there is no kinetic energy. In the system, with no energy loss due to heat, permanent set, or etc. The equation reduced to W equal to E, that is the elastic strain energy, also denoted by U. Hence, the force, hence for the conventional structural system, W equal to U, that is the work done is equal to strain energy. Strain energy is per unit volume is U, that is of times sigma into psi. Total strain energy is U equal to of time 0 to L integral sigma and psi into dV, where C is the stress and psi is the strain. Real work and complementary work is the two thing which is indicated in the strain energy method. Work equal to force times displacement. Work done as a force F moves through a distance delta. So delta W equal to F into d delta. Total work done W equal to integral of force into d delta. If the force F is three-dimensional with component Fx, Fy, Fz, total work done W equal to integral of Fx d delta x plus integral of Fy d delta y plus integral of Fz into d delta z. In this work is known as real work. From the graph, the x-axis delta, y-axis is force. So total real work or complementary work will be W integral of F time ds. Coming to the complementary work, delta WC equal to delta into df, that is the total complementary work WC equal to integral of delta x. It is the area above the load deflection curve. In linear elastic analysis, load deflection curve is linear as shown in the figure in the graph. Real work equal to complementary work, that is W equal to WC equal to 1 by 2 times of force into deflection. The area below the graph is equal to area above the graph. So expression for the strain energy for linear elastic member, we have four conditions. One is axial load member, member under bending moment, member under torsional moment on the circular cross section area, member under shear force on the rectangular cross section area. And first we go with the axial load member. U equal to of sigma into psi, that is the integral of sigma into psi into dV, that is the volumetric strain. So U equal to half time sigma into E will be sigma by E dx dy dz, where F equal to external force or load, A is area of the bar, L equal length of the bar, E is equal to Young's modulus of the modulus of elasticity. For a member for a length of L, the stress will be force by unit area F by A. Integration of dy dx equal to area, cross section area. So by applying this, U equal to half times integral of F by A into F by AE into dx A. So finally, you will get half time integral of F square L by AE. That is integral of dx equal to L. Coming to the member under the bending moment, From the pure bending equation, we know M by I equal to sigma by Y is equal to E by R, where M is the bending moment, I equal to moment of inertia, sigma the bending stress, Y equal to most distant from point from the axial middle axis, E equal to model of elasticity, R equal to radius of curvature. So strain energy equal to work done, which is equal to half time moment on angle turned through its axis. Usually called as in radians. So sigma equal to M by I into Y, integral of half times 0 to L, that is integral of 0 to L, M by I into Y. So we'll get E by I integral of M square dy by d I square. So finally we'll get U equal to 1 by 2E integral of M square by dx. Member under torsional moment on the circular cross section, strain energy equal to work done is equal to half time T into d theta. T equal to torsion, D equal to rotation angle theta. If the strain is U equal to half time shear stress into shear strain into volume. So finally we'll get integral of U equal to half time integral of TR uh, integral of 1 by 2 G integral of T square into dx. Remember under the shear force on the rectangular cross sectional area, V equal to shear force, I equal to moment of inertia, B will be width of the cross section, G will be shear modulus. So tau xy equal to VQ by IB, that's the shear stress equation. Strain as U will be half times integral of VQ IB dot VQ IB into G. So finally we'll get U equal to half into 1 by G R square dx into AS. So this is the four things of strain energy equation for axial load, bending, torsion, and shear. So we'll see in next class.